Now we're gonna do a titration of a weak acid with a strong base. The weak acid in this case is gonna have a 0.1 molar concentration, and we're also gonna have 60 milliliters of our titrant D or analyte. And because we don't know how much it dissociates, we're gonna have a K value that we need to use. So if we had H plus, I'm gonna do it in white. Oh. If we had H plus, HCl will dissociate 100%, right, into H plus plus Cl minus. In this case, we don't have that. We have HAC, which we normally call that a weak acid, right? That's acetic acid. So we are going to get, again, H plus, but very little, plus AC minus, again, very little. Most of it is going to be HAC. How much does it dissociate? We don't know. We have a constant that is that constant that will tell us that it's going to be a dissociation constant that is going to tell us the ratio of the products divided by the reactants. What is it? It's a ratio. And you all know ratios, right? You all understand ratios. If these are products and these are reactants. If I have more products than reactants, what does that mean, Autumn?
That it's so strong.
That's strong because it dissociated, right? Most of it dissociated. So that number, Ka will be greater than 1, right? If the numerator is bigger, the result will be greater than 1. If, on the other hand, like now, we're going to have mostly reactants, because this is an equilibrium, and it's going to be mostly reactants, very little products, then your denominator will be bigger. The concentration of the acid will be bigger. Ka for us is going to be less than 1. In this case, it's much less than 1, right? It's 1.8 times 10 to the negative 5. It's just a constant. Those constants are in tables. You can Google them. They will be given to you. And you can use them to solve these problems.
Wait, so if the products are...
If the products are
greater,
then it's a strong acid because that means, and the Ka will be greater than 1. If the reactants are greater, then it's a weak acid, and the Ka will be, or the constant for the acid will be less than 1. And we're going to find the pH before we add any base, at the equivalence point, at the half equivalence point as we did before, but we're also going to find the pH just before the half equivalent and just after the half equivalence, and we're going to talk about that. And also the pH when we add excess. So we're gonna have 1, 2, 3, 4, 5, 6 sketches to do. So let's go to the first one. Oh, the first one is derivation of a formula. It's called the Henderson-Hasselbalch. Next. That's your Ka for the acid. That's the formula I have given you. We separate it. We say, hey, we're gonna say Ka. You're going to have your H and your ratio. You just break it up. We make them all negative. And then we realize, hey, negative log is the equivalence of P. P means negative log. So the negative log of Ka is pKa. The negative log of the hydrogen concentration is pH, because it's the negative log of H. And the negative log of this, we're just going to leave it like that. But we are going to say the pKa is equal to the pH plus the log of AC over HAC. Can you take it down? this log, it should have been negative. What I do is I move things around. The pH goes over there. And you get your formula that is called the Henderson-Hasselbalch formula. The Henderson-Hasselbalch. When are we going to use this formula? So in our chart, we have, before we add anything, we won't use it. The 3 points that were in the buffer region, that's when we use it. Anytime that you have conjugate base and weak acid, anytime that you have concentrations of both, that's what we call a buffer. You have a little bit of one and a little bit of the other. This is the easiest way to find the pH. So we will use it for those 3 points in the buffer region. And it's actually not that hard. The calculator does all the work. Now the first thing, I don't know if you were supposed to write the complete equation in your formula, but we have the complete equation, the molecular equation for the weak acid and the base. If I had to do the complete ionic, I will never dissociate weak acids or bases. Strong ones do, but weak ones don't. So I will leave it together. That's very, very important, as you saw in the egg lab. This one is a salt, it's a strong base, dissociates completely, has NaAA. This one will dissociate completely, has NaAA, it's again a salt. Water stays together. Your spectator ion is your Na. So your net ionic equation is the HAC, which will never break apart. Your OH are going to make AC minus plus H2O. That will be your net ionic equation. Now, the first point is before any base is added. So, next. In here, we're going to use something that last class we called a rise chart or an ice chart. We know our dissociation constants, products over reactants. We have our equation where we dissociate the HAC into H plus AC minus. We are going to start with an initial concentration of the acetic acid. And at the beginning, we assume there is no H pluses or AC minus. They're not. So initially, we say it's 0.1, 0, and 0. Everybody okay with that?
Wait,
Then
what?
there is
Wait,
going to
what
be,
did you say?
excuse me?
What did you say?
At the beginning, you are going to have initial change and equilibrium, right? So initially, we were given a 0.1 molar solution, and all we had was acetic acid, right? So we said initially we had 0.1 molar of acetic acid, right? Then we have no weak acid and conjugate base, right? Then the change is going to be when we don't know how much dissociates. In math, we call it X, right? So we're going to say, we're going to subtract an X amount. So we start with all the HACs I had, so many, 6 of them. How many dissociated? I have not a clue. But I said I'm going to subtract an X amount, and however many dissociated, let's say 1 dissociated, that one that dissociated is going to be in equal parts. So whatever dissociated, you're going to have the same dissociation. You had this X, it dissociates in the exact same amount. So that's what I'm putting here. What do I have at equilibrium? I just add those 2 columns up. 0.1 minus X is 0.1 minus X. 0 plus X is X. 0 plus X is X. That is what you have at equilibrium. Does that make sense? That's what you have at equilibrium. So if I replace this into my Ka expression, the concentration of the acid, the H3O, is X. The concentration of my acetate is X again, right? So X and X. The concentration of my whole acid is in the bottom, that is HAC, written differently. So I end up with Ka is equal to X squared divided by HAC. What is important here? To realize that X is the concentration of hydrogen ions. That's what I'm going for. My whole purpose in life right now is to figure out the pH. And pH is the negative log of the acid, the negative log of this. Whatever X is, that is gonna be my pH. So using your math abilities, we're gonna solve for X. X will be equal to the square root, right? X is a square, so I'm gonna need a square root. I move this to that side, and it's Ka times the concentration of HAC. Right? This goes to multiply over there. I take the square root on both sides, and I end up with that equation. What is X? Your hydrogen concentration. Now I can find the pH of this solution. So any weak acid or any weak base, the pH is the negative log of the square root of Ka times Ha or HAC, right? Does that make sense? That's what you do.
For any what?
For any weak acid, you won't do the negative log of the acid concentration, you'll do the negative log of Ka times HAC.
Always?
For us this year, yes, because we're gonna assume, the part that you all didn't ask. You see how here I didn't put the minus X? We're gonna assume that so little dissociates that the X is gonna be negligible.
Wait,
So we
you
don't.
do the
we
negative
don't.
log of the square root of it?
Yes, the negative log of the square root of these two multiplied, yes.
Wait, how do you find like the Ka again? Is that
The Ka is given to you,
So you.
and the initial concentration is given to you.
So you do the Ka times the initial concentration,
Square root of that,
right?
negative log of that. Go ahead and do it, and make sure that you
Wait,
can
okay.
find that. Get your calculator out.
Yeah.
I need to make sure you can use your calculator and do this.
So you're always gonna do Ka times the initial concentration.
For weak acids, this year. Eventually you may find that this X is actually important in some cases when it doesn't dissociate as much, right? And I've had some students that regardless of what X is, they use their calculators. It will be a quadratic equation most of the times, and that's what I don't want to work on this year.
So.
But you'll just have a quadratic equation and you'll solve it. You can use your calculator and it will immediately spit out an answer. You don't even need to do the quadratic equation. You can do it with this one, and you'll realize that for the problems that we are gonna work, the X is gonna be negligible every time. If Ka was much smaller, you probably like 1 times 10 to the negative 1, you couldn't do that. But we're not gonna use those, yes. This is before you add anything. Before we added anything of a strong acid, we just did the negative log of H, done, right? Here, our H has to go through this process because we don't know how much dissociate. This is how much dissociates, right? I had to go through this process to find out how much dissociates, and then I take, that will be my hydrogen concentration, right? Once I find my hydrogen, this is only for weak acids with nothing added to it, right? Nothing added to it. Everybody okay with that? All these questions are good questions. This is not what I consider an easy topic. And getting lost in here is very easy and very expected. So do feel like stopping me anytime. Now we're gonna calculate the pH at point B. Now we're gonna drop 2 OHs. What happens when I drop an OH? It makes water, right? What happens when I drop the other OH? It gets rid of this H, of these pluses. It grabs them and it makes water. So I dropped 2 OHs and I had 2 leftover acetates. That's important to know. Every OH I have will leave behind an AC minus. AC minus is the conjugate base of HAC, right? This is HAC. Every time I drop an OH, I cancel the H and I'm left with an AC minus. This conjugate base is basic. The conjugate base Cl minus It's negligible. It's really not basic at all, right? But AC minus is. That's the reason we have a buffer. We start having a buffer. We are starting to have conjugate base and weak acid present together in the reaction, right? Right? What do we use when we have weak acid and conjugate base? We're going to use the Henderson-Hasselbalch equation. So go ahead in your first drawing. You are going to draw 4 HACs. You are going to draw 2 AC minuses. Forget about the water. But how many OHs did I drop? 2. So you have to drop 2 NAs, right? You're going to draw 2 Na pluses. Because you drop 2 of those, these are useless, the Na pluses. Those are the conjugate acids of a strong base. You got your drawings? You have 4 HACs, 2 AC minus, the waters, forget them, 2 Na pluses.
Is that point B?
That is point B, yes.
Wait, are the NA spectators?
Yeah,
Why do you draw them?
because the worksheet that was made by my friend, he wanted you to draw them. But I tend to not like to draw them as much because they get too confusing, right? But I want you to know that they did fall, they did drop, and since this is the first time we do it, I actually agree with his reasoning. That is the first time we're dropping something, the very first time you should do it so you know it's present. The Na pluses will be present in that solution. Now forget hydrated shells and all that other nonsense. So at this point, now let's go ahead and calculate it. Next slide. Next. My weak acid stayed the same thing. 1 molar, 6 milliliters, 6 millimoles, right? That's what I had of the weak acid. The base, 0.1 molar, 20 milliliters, 2 millimoles of OH minus, HAC. If I drop 2 OH minus, how many AC minus do I have? David.
4.
If I drop 2 OH minus, 1 and 2, how many AC minus were left over? Every OH minus cancels an H and leaves behind an AC minus, right?
2.
2. Every time you drop an OH, that OH will cancel this and leave out an AC minus, right? Very important concept. For every OH minus, I have an AC minus, right? So what will be my concentration of AC minus? 2 millimoles. And that's important because that's my base. So this is my base and this is my acid. Right? You do 6 millimoles of acid, subtract the 2 OHs that were dropped, I am left with 4 millimoles of weak acid, right? And I'm left with 2 millimoles of AC minus. In order to find the concentration, I need to divide them by the total volume.
Wait, how did you get 2 millimoles of AC minus?
Because I said for every OH that I drop, I'm left behind with an AC minus, right? That's the important part, that's the confusing part, that's the part that you need to realize, yes.
So whatever.
Why in the first one do you use the ice charts, but not in this one?
In the 3 other ones, you can use ice charts. I just prefer to understand it like this, but you could use ice charts. And I'm gonna use the Henderson-Hasselbalch for everyone that you have weak acid conjugate base. I'll use Henderson-Hasselbalch. To me, it's the easiest way to do it. There are a million ways to solve these problems, a million ways, literally. I wish acids and bases were more strict, but this is what I find works the best, but we can do ice charts as well. Now, you have 2 millimoles of acid. If I wanted to know the concentration, I will divide it by how many milliliters?
80.
80. 80 milliliters. I'm gonna put one over the other, the base over the acid, right? That's the base. So I'm gonna put this one divided by this one. If you have 80 in the numerator and 80 in the denominator, what's gonna happen?
It's gonna be 1. Wait, so
They're
you're
gonna
solving this-
cancel. So I'm not even gonna divide them. I'm not gonna find the concentrations. I'm just gonna use the millimoles straight. They should be concentrations, but since they're over the same volume, they cancel. Do you see what I'm saying? This should be a concentration of the base. It should be 2 divided by 80, and it should be 4 divided by 80. But I tend to, and you can do that, and it's perfectly all right. But if you are dividing by 80 and by 80, the 80s are gonna cancel. So it's literally 2 divided by 4 for that. So go ahead and put this in the calculator. You're gonna, what does P mean? Negative log. So take the negative log of 1.8 times 10 to the negative 5. And you're gonna add the log of 2 divided by 4, this is 0.5. You can do concentrations if you want, it's just not necessary in this particular case. All the buffers, you just can put moles. So the log in base 10, you have a thing, you need to do it in your calculator, David. I need to make sure that you know how to do this. Because seeing it is not the same as doing it. Everybody, I wanna see your numbers in your calculator. Elizabeth, I need to see the number.
I just have my calculator on my thing. I don't have
So I need to see your number in that calculator.
Wait, what am I doing?
I want you to solve for the pH. In your calculator.
Is it not the same as what we just... Can I not use this?
You have to
negative-
use, no. The buffers use the Henderson-Hasselbalch. You have acid and you have base. In the one before, we only had
Okay,
acid,
wait, yeah,
right?
got it, yeah.
This one has acid and base. You have the 3 points right after the first point and before equivalence are gonna be a buffer solution. You're gonna have acid and base. So you do 0.5 and then log 10 of that. In your calculator, you have a button that says log, right? So it's 0.5. Where's your 0.5? Oh, you can put log of 0.5. Because 4 divided by 2 divided by 4 is 0.5. LOG is log index 10. LN is not, right? LOG is assumed already to be base 10, right? LOG is base 10, so the bottom that you see LOG in your calculator is base 10. The other one is the natural log and it's LN, it's a different button, right? Everybody got that?
Wait.
Okay, now let's move to the next point. Oh, I put this later.
Wait, what's the final answer?
4.44.
I
That's
got
what.
7.44.
So,
Is those, like concentration, do you mean the millimoles or the molarity?
so what I said is, if you use millimoles and divide it by 80 for both of them to do concentrations, the 80s are gonna cancel out, so you can just put millimoles.
What is the molarity? For
Excuse me?
Concentration.
For concentration is molarity, yeah. Because it will be millimoles divided by milliliter, right? So the millis cancel and it's still moles over liters. It's a ratio, it's the same ratio, right?
So are you gonna use this like now? Always?
For buffers, always, for those 3 points. So let's go to the next slide. For these for any point, when you start adding acid and you have just after A and before E, that you have weak acid and conjugate base, you're gonna use the Henderson-Hasselbalch, right? Now point C, let's go next. You do the same thing. You're gonna have next 0.1 molar, 30 milliliters. and you always have the same amount of acid, right? Same amount of acid. You always have 6 millimoles. But this time, if you go there, you're gonna be dropping half, 30 milliliters. We subtract them.
Are we at the half equivalence point?
We are at the half equivalence point because you have half of them were, you see, half of them were neutralized. The other half is not. So we have the exact same amount of weak acid, the exact same amount of weak acid as conjugate base, right? The exact same amount. Can you see that? Same amount of weak acid as conjugate base, right? So you, in your drawing, you should have this plus your 3 NAs. Everything is 3, 3, 3, 3. You have 3 acids, 3 conjugate bases, 3 NAs. When we use the Henderson-Hasselbalch, you're gonna have that the pH is gonna be equal to the pKa plus the log of the base over the acid, right? If this is 3 and this is 3, is the log of 1, right? Anybody knows what's the log of 1? What? Anybody knows what the log of 1 is? 0. So this term cancels out, right? So pH equals pKa at the equivalence point. Yeah, you can memorize it, but I want you to understand where it came from. Do we understand it?
So then it would just be the negative log of...
The negative log of 1.8 times 10 to the negative 5, yes. The pH is gonna be 4.76.
Is that always the same, like the 1.8 times 10 to the negative 5?
That's the Ka for acetic acid.
Oh, so it changes every...
It changes depending on what acid we're
Are you
using.
gonna give it to us?
Yes, that has to be given.
I got 4.74, not 4.76.
You got 4.74? Well, maybe I calculated it wrong. So I'll go back and check on that. 1.8, the negative log of 1.8 times 10 to the negative 5, it may be 4.74. Sometimes my
Yeah, that's what
eyes, yeah? So I'll go back and change that. Sometimes I look at my calculator. I need glasses. I have glasses now, actually. So at this time I'll use them. Next slide. Now we're gonna go to point D. Exact same thing, we're still in the buffer region, but we've added 40 milliliters of base. So next slide. You have 40 milliliters of base, same 0.1 molar, 4 millimoles, same amount of acid, 6 millimoles. You drop 4 OHs, Reese, so how many AC minus do I have if I drop 4 OHs? 4, because every OH leaves behind an AC minus. I subtract them, I get the acid. Acid goes over here, base goes over here. And when you do this, hopefully you get 5.05. Again, you can divide it. The total volume here is 100 milliliters. But because you are dividing over the same volume, it cancels out. So you can or cannot. But if you want to stay true to the formula, it is concentrations.
Wait, how do you know you got 4 millimoles of AC minus?
Because every time I drop an OH, I'm left with an AC minus. And since I dropped 4 OHs, I'm left with 4 AC minuses. The OHs cancel and make waters, so I'm left with 4 waters. Every OH made a water with an H, right? So for every OH, I'm left with an AC minus.
Wait, how do you get that again? A minus? You divide?
The A minus is the concentration of your base, but you don't have, just go ahead and divide by 100. And the HA is the concentration of your weak acid. It's actually the conjugate base. That's the reason we are doing buffers right now. Is the conjugate base divided by the weak acid, log of that, plus the negative log, P means negative log of your Ka, and your final answer should be your pH. Everybody okay with that? Your sketch should have 4 NAs. For every OH, there should be an Na. And they should be really little because they are ions of a metal, right? They're cations, which tend to be smaller. Everybody okay with points B, C, and D? Same equation, right? Now let's go to the next point. E. What is E? Equivalence. What happens at equivalence? All my H's disappear. Did you see that? No H is present. What do I have left over in solution? AC minuses, all conjugate base. Should the pH be 7?
Yeah.
No,
No, it should not.
because it's base. This conjugate base matters. The Cl minus does not. Who cares about that one? The conjugate base of a weak acid, of a strong acid is useless. It's a